All right, thank you very much. So my name is Jonathan Magnusson, and I'm a PhD student at Karlstad University, and I'm going to present some of the research that I've been doing lately. Let's see if this works. All right, a little bit short. Who am I? So Jonathan is my name, PhD student, and the research that I'm doing at Karlstad University is funded or sponsored by the Swedish Internet Foundation. And it also happens that I'm also a new first-time attendee at OARC, which is very fun. I recognize some of your faces from hackathons and other things, but it's fun to be here for the first time. So, getting into the privacy and security of DNS resolvers. So, when starting this study, I had to scope the research to look at what can I do in the setting that I have designed for this study. So I looked at mainly 5 different mechanisms in DNS resolvers that I can evaluate using the RIPE Atlas network. So I will get more into that later. So the first one is IPv6 capabilities. Many people don't connect this with security or privacy, but to a degree, it's all about availability. Your resolver being able to query a name server over IPv6. Then we also take a look at DNSSEC validation, very common. Then also query name minimization. Then we have the eDNS client subnet. So when a resolver is sharing part of the client subnet, in the context of privacy, we invert this metric. So we call it no ECS. So we see if a resolver is not sending this information. And then we also look at minimal responses from the resolver back to the client. So we perform some active measurements using the RIPE Atlas probes that you might be aware of. So it's a global network of volunteer probes, and they all have pre-configured resolvers. So it could be a local resolver that's running on the same network. It could be the DNS resolver provided by the ISP, or it could be a public resolver. So our setup when doing these measurements is that we have a bunch of probes, and these probes have configured one or more resolvers. And then we also have control over the other side of this measurement, the authoritative side. So we can take a seek and send active measurements, some queries, and then we look at the responses, and then we can see what are these resolvers adopting. We're also aware of that these resolvers can also forward queries. So if you send a resolver, it could forward the query to yet another resolver before reaching us. So we made this beautiful little map where you can see that the probes might have 3 different categories of resolvers, as I mentioned, the local, the within same AS, which is usually an ISP provided resolver, and we also have outside the AS, which is a public resolver. And then we can see what is reaching us at the authoritative side. So I hope you remember your flags. So we have the different countries where we have Denmark, Estonia, Finland, Iceland, Lithuania, Latvia, Norway, and Sweden, where we are today. So we found a bunch of probes. They all have a different amount of configured resolvers. So we had a total of a little bit over 1,000 probe/resolver pairs to work with. So we looked at the different forwarding configurations, and we could see that if the pre-configured resolver is sitting on the same local network as the probe, then it's very likely to forward the query to a resolver within the same AS or outside the same AS, compared to resolving the query itself. And then we saw that when it's configured to use within the same AS, then it's very unlikely to forward it to yet another resolver. And then we see for the public, it's not going to forward anything, usually. And then we take a look at the feature adoption for these probe-resolver pairs. So when looking at all these 5 dimensions that are presented in the beginning, we saw that there was a very high or relatively high adoption rate of over 70% for all of these. But now we want to also break it down, since we can categorize the resolvers into the private, the AS, and then the public resolvers. Then we saw something that was very interesting. It was that for the public resolvers, we had a very low adoption of query name minimization, not using ECS, and also minimal responses. So that was, that's interesting. So let's take a look at some of the more popular providers of public DNS resolution. Here. So then we had Google, Cloudflare, and Quad9, which represent around 90% of the public resolvers. And we saw that for the Google public DNS, then we had 0 adoption of query name minimization, which was strange. And then we saw that only sometimes it avoided sending the eDNS client subnet, and there was no minimal responses coming from it. So in a previous study that we did around query name minimization, we set up this domain that we use for querying it from the client side. So we send a query, and then we get back a TXT record, which responds hooray if it's query name minimized query, or it says no if it doesn't. And setting up these different, so these are different domains for different studies over time. And the one at the bottom, the third one that we're using, then it said that if we query the public DNS of Google, then it's responded with no. And the main reason behind this is that when the public DNS of Google is minimizing queries, it does it at the root and the top level domain. But since we have setting up our measurement at labels A and B, it means that we cannot see this minimization going on, which is a limitation of our approach. But very important to keep in mind when looking at these numbers. All right, moving on. So after looking at the public resolvers, we also wanted to look at, since the private resolvers that are local close to the probe, it is very likely to forward queries to yet another resolver. So let's take a look at these different configurations, see how they adopt. Yes, here we have it. So looking here at the final table, we can see that when we are forwarding queries from the private resolver to a public, for example, we can see the adoption of IPv6 going up to 100%. So that's something that the private to private, or when we have a single resolver that's doing the resolution, then it's very low. And then we can see that it's around 100% for not sending the client subnet and also providing the client with a minimal response. So since we are looking at these Nordic and Baltic countries, you remember the flags, right? So then we do some analysis by country as well. So here's the feature adoption by country. And we can see that we have various number of pairs. First of all, pairs keep in mind, but also we have various adoptions. So we have Finland having a very high adoption of IPv6 capabilities, Iceland 100% DNSSEC, and so on. So we have some very nice high numbers here. But then we also wanted to take a look at, since we have private resolvers, right, that are probably set up by the same person running the RIPE Atlas probe. So maybe they're biased in how they set up this resolver and configured in a certain way. And at the same time, if these probes are using public resolvers, that might not be representative of the countries themselves. So we take a look at the AS resolvers, those usually provided by the ISP. And then the numbers shift a little bit. So here you can see the Norway has a very high IPv6 and minimal response adoption, DNSSEC very high in Denmark, and query name minimization in Estonia, and it's like 100% all down the board for not using the ECS, which is very nice. Bears in mind that even though Iceland has a very much 100%, there's only 2 probe resolver pairs in the study. Yes. Then we also did some correlation analysis. So we looked at the different features and saw, okay, if a resolver is adopting a certain feature, what is the likelihood that they're also adopting others? So here's a nice little heat map where you can see the different features. A 1 represents a like a strong correlation between the features, and a -1 is negative correlation, and then around 0 is like, doesn't really matter. So we saw some correlation between DNSSEC and IPv6, so those seems to be very commonly collocated. And then around the data minimization type of features, the query name minimization and NCS and MR. But here we also have all probe resolver pairs. And since public resolvers are very popular, then they may skew this kind of analysis. That's why we also take a look at the individual unique resolvers as well. So we have a new heat map. Here we can see like slightly lesser, like so a bit weaker correlations, but we also see a new one pop up, which was not there before, which is between query name minimization and DNSSEC, which was a bit fun of a find. Still, the strongest correlation between any 2 features in both of these analyses was the minimal responses and query name minimization. All right. So in conclusion, we have a high adoption rate, looking at all the probe resolver pairs. It varies between what type of resolver it is, how close in network proximity it is to the probe. We have some like a leaderboard of different features here, and everybody wins at not using the ECS. And we also find some nice feature correlations between these. All right. For future work, it would be fun to look at this over a longer period of time to see if it changes. Also expand the scope of features, because now we're only looking at 5. We are a little bit limited of what we can do with RIPE Atlas, and that's why it's important to also look at the representativity of these probes and maybe looking at alternatives for doing these types of measurements. All right. Thank you very much, and I'm open for questions.
This is Peter Thomason. Welcome to the OARC community.
Thank you.
It's been a great talk. I have 2 comments or questions. So if I understood correctly, you set up a zone that has DS records but isn't signed, and that's your DNS-SEC test?
Yes, that is our initial DNS-SEC test. Oh, I know that you can do much more tests around this.
So your measurement is essentially that if you get serve fail, then you assume that DNS-SEC is supported?
Yes, that is the assumption for this test.
Okay, so there is a bunch of RIPE probes, I don't know, maybe 5% or something, that serve fail anyway. So the test might be inaccurate, and you might want to maybe add something that controls for false positives like this by also setting up a zone that is validly signed, and maybe like some common thing like RSA, and then check for the AD bit or something and the expected answer content like IP address, for example, because in tests that we've done last year or 2 years ago, we sometimes got an AD bit, but the wrong A record or something. So it's quite interesting. So that's just like a side comment. And the second is I was confused by the low correlation between DNS-SEC and QNAME minimization, because if I recall correctly, QNAME minimization is not done by Google, but by Cloudflare, for example, and they also do DNS-SEC. And so I would have expected more than 0.05.
Yeah, we only count, so we did the, let's see, can you go back to this one, right?
Yeah.
So between the kernel minimization and the DNS-SEC, right? In the first one, where it's not normalized.
Ah, okay.
Yeah, and then the second one, which is normalized.
Okay. I think when you talked about the right-hand side, I was writing down my note. So.
Okay, thank you.
Petr Špaček, I see. Thank you. I wanted to point out that some of the public resolvers behave differently for different names and for different levels of hierarchy. Did you account for that, or did I miss that? Or
we have not taken into account for that for the public resolvers.
Okay, then perhaps you can talk after.
Yeah, sounds great.
More questions? Anything remote, Alex? No. No? Maybe.
I'll take the mic.
Yeah, see? There you go. You can do your shot.
I'm really sorry about this. I made a joke in the workshop room. Hashtag question, which is not really a question. Could you go to slide 1, which is your second slide?
Is there not a reset?
Yeah. There you go.
This
more?
one?
No, one
and
for
this one. Yes.
Why do you have a coffee cup in a server room?
Touche. It's not my servers.
It's not It's his bedroom.
And even worse, we reviewed the slides and didn't come up with that criticism.
Oh, there's still a question. There is a question. The mic is all sad. Let's see. How were the Atlas probes selected internally and for repeated measurements? Asks Andreas from
Could you repeat the question?
Yeah. Oh, sorry. How were the Atlas probes selected internally and for repeated measurements? Initially, yeah.
Yeah, so for the RIPE Atlas probes, if we take a look at the next slide here, right? So these are the RIPE Atlas probes. So then we take like a look at the amount of available probes for all the different countries that were in the scope for this study. And then we selected all of them that we could. After some initial measurements, we took a look at, okay, what type of weird behavior do we find for some of these probes? And should we filter some of them out for our measurements. So one was, for example, that in order to do some of the correlations between the client and the authoritative side, we needed to have a nonce that was sent over. And sometimes a few probes were behaving weird, where they sent the same nonce to all of their resolvers, instead of generating a new one for each, which is the expected behavior. So then we had to filter those probes out. And then we also included the probe resolver pairs that were able to do all of our 5 dimensions of measurements in order to compare them with each other. So we did some selection, and I have some details around that if that's interesting.
Okay, cool. So just to be clear, that was Andreas doing DNS offset at Hetzner.
Thank you.
No further questions. Thank you, Jonathan.
Thank you very much.